Welcome to Fromobius. Today we are taking a microscopic leap into the fundamental architecture of artificial intelligence. When you read the latest research papers or boot up an open source language model on your laptop, you will consistently hear the exact same terminology used to describe their power. You hear words like 80 billion parameters, 200 billion parameters, 1 trillion parameters. This episode is inspired by the brilliant engineering team at ngrok and their deep dive into how these numbers actually work. But what are parameters? When you strip away the massive server clusters and the bleeding edge hype, what are you left with? You are left with an enormous graph of carefully arranged mathematical operations. Let us isolate exactly one operation. It begins with an input number. This could represent the brightness of a single pixel in an image or a specific metric evaluating a word token. We pass this number, say 2.0, along a mathematical connection. This connection holds a value. That value is the parameter. In this specific context, we refer to it as a weight. Let us give this weight a value of 0.5. The computer takes the input and multiplies it by the weight, yielding a single output. In this case, 1.0. This atomic calculation is the pulse of modern computation. By passing billions of input numbers through billions of multiplying weights, the engine transforms raw data into language, logic, and art. The math here is as simple as y equals w times x. However, simply multiplying numbers is mathematically insufficient. If an artificial brain only knew how to multiply, it would be strictly linear. It could never trace complex curves, loops, or human decisions. It needs two specific mathematical upgrades. The first is the bias. A bias is an independent parameter that sits beside the weight. It is not multiplied by the input. It is simply added to the output. While the weight scales the volume of the signal, the bias physically shifts the entire activation threshold left or right, allowing the model to trigger an active response even when the input value is extremely low or completely zero. Without bias, every line must always cross the origin. The second required upgrade is nonlinearity. This is normally achieved using an activation function such as the rectified linear unit, commonly referred to as ReLU. It is deceptively simple. If the final calculated number is less than 0, force it to exactly 0. If it is greater than 0, leave it alone. This simple clamp is what allows a neural network to bend its logic and solve complex nonlinear realities that humans experience. With our single parameter equation complete, we can zoom out. As intelligent models train, they compile millions of these equations simultaneously. Doing this one by one is far too slow for normal processors, but perfectly suited for graphical processing units. To feed graphics cards optimally, engineers convert the node arrows into massive arrays of numbers called matrices. Those overlapping lines represent the weights. We can cleanly reorganize them into a dense sheet of floating point numbers. Think of a grid where every row and column corresponds to a specific structural connection. This matrix is quite literally the artificial brain. When we say an LLM is 80 billion parameters, we definitively mean 80 billion exact floating point decimals, locked inside grids identically structured like this one. Now you know exactly what a parameter is physically doing under the hood. But how do these massive grids of floating point mathematics decide to actually output probabilities? How do they safely predict the next word when you ask them a question? That introduces the softmax function, and we will cover exactly how that works in episode 2. Subscribe to Fromobius to ensure you do not miss it. Thank you for watching.